All right, so today we continue with the topic of the Cayley-Hamilton theorem. Let me remind you, so recall, let me use a different color. Recall from the last lecture, we have defined what it means to evaluate a polynomial on a linear operator, right? So recall, if we have V, a vector space, and we have let's say T, a linear operator on V, okay, and where V is a vector space over the field of scalars F, okay, then and if we have F of T, little t, the variable, a polynomial with coefficients in the same field F, okay, then we have defined a new linear operator in terms of this given data. Then the linear operator f of t, okay, so which we also refer to as the evaluation of the polynomial on t, is defined as follows. So it's defined by simply intuitively, we just utilize this linear operator as if it was a value of the variable of the polynomial, right? So it's defined as f of t is equal to a0 times the identity operator on V plus a times a1, sorry, times t plus etc. plus an times t to the power n, okay? Where, of course, whenever we write the power of a linear operator, this is the composition. So this is t composed with t, etc. So composed with itself n times. Okay. So the point is that f of t is also a linear operator defined in this manner. Okay. All right. So this was where we stopped last time. So now we can state the Cayley-Hamilton theorem. So this is theorem 523. The Cayley-Hamilton theorem. Okay. So the situation is the same. Assume we have T, a linear operator on a vector space V, where V is a finite dimensional vector space over a field of scalars F. Okay. And let now f of t be the characteristic polynomial of t. Okay, so it's a particular polynomial which we know, the characteristic polynomial t of this linear operator t. Okay, then we claim that if we now evaluate this characteristic polynomial on the t itself, yeah. So f is the characteristic polynomial of t, and we evaluate it on t itself. Then the resulting linear transformation is going to be t0, which is the zero linear transformation, or the zero linear operator on V. Okay. So what do we mean by this? So this is simply the linear operator that sends everything to zero. So t0 of x is equal to 0 for all x in V. Okay. So informally, we can say that what it means is that the linear operator t is the root of its characteristic polynomial. Okay. So let me write it in quotation marks. So one way to remember this is that t is a root of its characteristic polynomial. Right? Because if you evaluate the polynomial on it, you get 0. So 0 here in the sense that this is the zero transformation, the zero linear operator. All right. So this is the statement of the theorem. Okay. Everyone is okay with the statement? So if yes, then let's go ahead and prove it. Okay. So what does it mean to show that some linear operator is the zero operator, right? So it means we have to show that it sends every vector to zero, okay? So we have to show that if I take the linear operator f of t, okay, and apply it to a vector v, then I'm going to get the zero vector for all vectors v in v, right? So this is what it means to be the zero linear operator. So we have to show that f of t sends every vector, excuse me, sends every vector v to zero. Okay, that's the task. Okay, so first of all, this is clear when v is zero, right? So if v is the zero vector in v, then this is clear because we know that f of t is a linear operator, right? We know that f of t is linear. And this was by theorem E.3a that we discussed last time. Yeah. So we know that every linear operator sends 0 to 0. So for v equals 0, this is just linearity. Okay. So from now on, we may assume that v is not 0. Because for v0, we are done. Yeah. So we assume v is not equal to 0. All right. So now let's analyze what happens in this case. So take a non-zero v, okay, and we let w be the t-cyclic subspace of v, okay, generated by this vector little v. Okay. And we let k be the dimension of this cyclic subspace. Okay. So again, let me remind you that the cyclic subspace, this just means that this is the span of the vectors v itself, t of v, t square of v, etc. Right? So it can be finitely many vectors, can be infinitely many, doesn't matter. Okay. So this is the t-cyclic subspace, and we take k to be the dimension of w. And note that we know that k is a number, right? Because the dimension of w is finite because it is a subspace of v, right? So this k is less or equal than the dimension of v, and we're assuming that v is finite dimensional. So this tells us that w has some finite dimension, so we just denote it as k. Okay. All right. So we have the cyclic subspace. So now we know how to determine the basis and the characteristic polynomial for restriction to this subspace. This was the topic of the previous lecture, right? So by theorem, what was it, 522a, which we proved last time, we know that there exist some scalars, a0, a1, etc., through a k minus 1, right, in F, such that we can write a0v plus a1 t of v plus etc. plus a k minus 1 t k minus 1 of v plus tk of v, right, is equal to 0. So we know this happens because, again, remember by theorem 522, we know that these vectors, v, t of v, etc., all the way up to tk minus 1 of v, they form a basis for w. So hence, tk should be given by some linear combination. So we have such a linear combination, right? We have a choice of the AIs like this, right? Okay. So also, the second part of the theorem, so by theorem 522b, we also know how to write the characteristic polynomial, right? So we know that the characteristic polynomial of the operator t restricted to w, right? The restriction to this cyclic subspace w is given by, let's denote it as g of t. So it's given by minus 1 to the power k, where k, again, remember, is the dimension of w. So minus 1 to the power k And now we use the coefficients from the previous line. Yeah, so we have a0 plus a1t plus etc. plus a k minus 1 t to the power k minus 1 plus tk, right? So this gives us the characteristic polynomial of the restriction of t to w. Okay, so here I just applied the theorem. All right, so now we have these two equations. Yeah, so we have the first one that this is equal to 0. This is the first equation, and we have the second equation, which gives us an expression for g. Okay, so let's combine these two things. So I'm going to the new page. Okay, so let's calculate gt evaluated on v. Okay, so note here is a capital T, right? So we take our linear operator t and we plug it into g. Okay, all right. So by definition of what it means to evaluate a polynomial on a linear operator, this is going to be minus 1 to the power k a0 times the identity operator, right? So we have the identity operator I plus a1t plus etc. all the way up to a k minus 1 t to the power k minus 1 plus t to the power k. Okay, so all of this is just g of t, right? Because we know what the polynomial g looks like. Well, we know the coefficients a0 through a k minus 1. So we just have to substitute to plug t into it. Okay, so this gives us g of t. And now I want to still evaluate it on v, right? So I still need to evaluate it on the vector v. All right. So but now we just use linearity, right? So here we just use linearity. So this is equal to minus 1 to the power k, still the same coefficient. But now we just need to apply this operator in the brackets to v, okay? So first I apply a0 I to v. So I is the identity, so I of v is v. So a0 I of v is just a0, right? Times v. Plus, similarly, we get a1. This is just t of v plus etc. Plus a k minus 1 t to the power k minus 1 of v plus t of v. Okay. So this gives us the result of applying this linear operator to v. But now look what we have here in the brackets. So this expression here in the...
Shouldn't it be t to the k of v?
Oh, excuse me. Yes, it should be tk. Thank you very much. Yeah. Yeah. All right. So now look at what we have in the brackets here. Let me go back for a second. So look at this equation. Let's denote it star, for example, right? So remember how the coefficients a0 through a k minus 1 were chosen. They were chosen to make sure that this is equal to 0, right? So now if I go here, what I have in the brackets is exactly star, right? The same expression. So this means that the whole result of what I have in the brackets is equal to 0. Right? So we get the answer is 0. Because the whole thing in the brackets is 0. All right? So this shows that if we evaluate the characteristic polynomial of tw on t, it sends everything to 0. Because v was our vector, right? Okay, but then we also know by theorem, it was 521. Sorry, let me write it again. It was 521. We know that g of t divides the characteristic polynomial of f, right? So we know that g of t divides the polynomial f of t, right? Remember, if we have if we take restriction of a linear operator to some subspace, then the characteristic polynomial divides the characteristic polynomial of the original operator. So we have g of t divides f of t. So what does it mean again? So this means there exists some polynomial q of t, let's say, such that we have f of t, right, is equal to Q of T times G of T. Right? This is we simply write out what it means for G to divide F. Okay. But then if we have, since we have such form for F now, we can look at what F of T does when we apply it to V. So this is the same as taking Q of T times G of T, right? Applying to V. Okay. But this is the same as Q of T times G. In fact, not times. We're taking the here we're taking the composition. Sorry, because remember, yeah. So we take Q of T times. Sorry, not times. I keep saying this. I don't know why. So Q of T composed with G of T evaluated on V, right? That's what we are getting here. And this we know is 0 by the above, right? So this is equal 0, as we just pointed out. So here, we know that this is 0. So then it means that we're applying the linear operator Q of T to 0, okay? But Q of T is linear, so it sends 0 to 0. So this is again 0, right? So simply because Q of T is a linear operator, right? So it sends 0 to 0. And so we get, look, what we started with. So remember, V was an arbitrary non-zero vector, right? So this was any non-zero vector in V, right? And we have demonstrated that if we apply the linear operator F of T to any non-zero vector, we still get 0 as a result. All right. So this shows that F of T sends everything to 0. So F of T is the 0 linear operator on V as wanted. Okay. So this concludes the argument. Okay. So you see, we used some of these previous results. We used the properties of the cyclic subspaces. We used our result about the characteristic polynomials of a restriction of linear operator to a subspace, etc. So all of this comes nicely together in this argument for the Cayley-Hamilton theorem. Okay. So any questions about this proof? I know it combines several things, so you might need a bit more time to look at it, but like at least at the first look, is it fine? Or if there's anything, let me know if something is unclear here. All right. So if not, let's first look at some example, and then we'll discuss a version of this for matrices, which as usual we have. Yeah. So let's look at an example. So we want to see this result apply to some particular, let's say, linear operator. So let T be a linear operator on R square, given by the definition. So we say T of AB is equal to, let's say, A plus 2B minus 2A plus B. Okay. So for defined like this for all AB real numbers. Okay. So just an example. So let us take beta to be the standard basis. So E1, E2, the standard basis for R square. Okay. And let's see what happens. So let's look at the matrix corresponding to this. So we look at the matrix representing T with respect to beta. Okay. So we know how to calculate this, of course. So this is going to be 1 minus 2, 2, 1. I'm not spelling out the calculation. I think you've seen it by now, right? So you just have to, yeah, as usual, just calculate the coordinates of the vectors T of E1 and T of E2. Okay, so we have this matrix representing it. This lets us now to calculate the characteristic polynomial, right? So then the characteristic polynomial of T is ft. So the formula is as usual. We take the determinant of the matrix A minus T times the identity matrix. So here it's 2 by 2, right? So, all right. So just plug in the values for A into this formula. So this gives us the determinant 1 minus 2, minus 2, 2, 1 minus T. Sorry, it was 1 minus T. I think I said 1 minus 2, 1 minus T. Yeah. So we have this, and calculating the determinant, this is simply T squared minus 2T plus 5. Okay, so this is the characteristic polynomial. All right. So then, if we want to evaluate this polynomial on T, right? This, by definition, this simply means we have to replace the variable of the polynomial by the linear operator. So we have T squared minus 2T plus 5 times the identity. So IV. Yeah. Well, IV, or where V, of course, is R squared in this example. Yeah. So we have this. This is the result of, well, this is f of t. Okay. So now by theorem E3 from the last time, if we want to look at the matrix representing the linear operator f of t with respect to beta, yeah, this is going to be the result of applying the polynomial f to the matrix representing t with respect to beta, right? So which is the same as f of a, because a in this example we denoted by a t beta. Okay, so now just plug it in. So we know f of t is here, yeah. So just plug the matrix into it. So we get a squared minus 2a plus 5 times the identity matrix. So 2 by 2 identity matrix. Okay, now we have to calculate it. So calculating, we get minus 3, 4, minus 4, minus 3, plus minus 2, minus 4. So you should check these calculations yourself. 4 minus 2, plus 5, 0, 0, 5. Okay, and so just now just add it up. Okay, so we get that this is 0. Okay, so we get the 0 matrix as a result, which means precisely that f of t is the 0 linear operator. Yeah. So in this example, we just verified the theorem, what the theorem tells us by hand. We just calculated explicitly the characteristic polynomial. We determined the result of applying it to t, and we have calculated, and we see that indeed we get the 0 linear operator as the theorem predicts. All right, but the theorem tells us it's always true, no matter what your linear operator t is. Okay, so it's an example. Next, as promised, we have, of course, as usual, an analog for matrices. So let's call it corollary. So this we can refer to as the Cayley-Hamilton theorem for matrices, as opposed to linear operators. Yeah, so Cayley-Hamilton for matrices. It's essentially the same. Yeah, so assume you have a matrix A, a square matrix, because we talk about linear operators. So square matrix over F, and assume that f of t is the characteristic polynomial of A. Okay. Then we have that f of A is equal to 0. Okay, so here 0, I should write 0. This is the 0 matrix, right? So the n by n 0 matrix, to be completely precise. So n by n 0 matrix. Okay. Proof. So here the idea is just to reduce it to what we already proved for linear operators, right? Using the correspondence between matrices and operators. So let's do it. So let A be a given matrix. So n by n matrix over F, let it be given. Okay. So remember, when we're given a matrix, we can always find the linear operator corresponding to it, the LA, right? So let LA remember, this is a linear operator on the vector space f to the m. Yeah. So let LA be the linear operator on the space Fn, which, as usual, we know it satisfies that the matrix representing LA is exactly A, okay, where beta is the standard basis. Standard basis for Fn, okay? So, and this linear operator, remember, it just corresponds to multiplying by the matrix A. Yeah, nothing deep here. Okay. So then recall that we have the characteristic polynomial of this LA. So the characteristic polynomial of LA is, by definition, the characteristic polynomial of the matrix A, right? So the characteristic polynomial of the matrix A, okay? And so if we look at f of A, so we evaluate the polynomial f on the matrix. Now by theorem, applying theorem E3, we know that this is the same as looking at the matrix representing the linear linear operator f of LA with respect to beta, right? So we have this, but we already know that applying f, evaluating f on a linear operator for whom it is the characteristic polynomial, we get 0, right? So this is just T, the matrix representing T0. We just proved this, right? So this is theorem 523. Okay, but T0 is the 0 linear operator. So it's a linear operator which sends everything to 0, right? So recall, this is the 0 linear operator on Fn. And of course, the matrix representing it is the 0 matrix. So we get 0, right? So what we have obtained is that if I evaluate my polynomial f of A, which is the characteristic polynomial of the matrix A. So if I evaluate it on the matrix A itself, we get 0, which is exactly the statement of the corollary. So we have again this parallel for matrices corresponding to what we have for linear operators. All right. Okay, so this is the Cayley-Hamilton theorem. So it's a neat fact, and we'll see later it actually is useful also for many questions of analyzing linear operators. But in order to see how it's used and applied, we need to talk about ways to decompose a vector space into smaller vector spaces, namely the operation of direct sum of vector spaces. So some of you might have seen it, maybe some haven't, so it doesn't matter. I'm going to review it in any case to make sure that we're all on the same page, okay? So we're going to talk about direct sums of vector spaces. So this is the next subtopic, okay? Let me begin with some definitions. So assume we have T, a linear operator on some vector space V, okay? So there is a way of decomposing V into simpler subspaces that offers us insight and better understanding into the behavior of this linear operator T. So the global strategy, without going into any details, the intuition is that given a linear operator, if you want to understand how it behaves, we want to analyze it by chopping the space into smaller pieces and analyzing how T behaves on each of the smaller pieces, which can be a simpler task usually, okay? So the idea is to subdivide or like divide and conquer, you know, this kind of, you want to divide our space into smaller subspaces and analyze the operator on each of them separately. So, and we will see that in the case when the linear operator T is diagonalizable, the simpler subspaces are going to be precisely the eigenspaces of this linear operator. But in general, it's going to be something more complicated, okay? But we'll get there. Before that, we need to talk about what do we mean by like a space being given by a collection of smaller subspaces. So for this, let's talk about direct sums first, okay? So assume I have a bunch of subspaces, let's say W1, W2, etc., WK. So let this be subspaces, finitely many subspaces of a vector space V. Okay, so assume I'm given a bunch of subspaces. Then we're going to define the sum of these subspaces. So the sum of W1 through WK is going to be the set of vectors of the following form. So we look at all vectors which can be written as V1 plus V2 plus etc. plus Vk, where we have that each Vi comes from the corresponding subspace. So it comes from Wi for all I between 1 and k. Okay, so we collect all vectors which can be written as sums of this form. And we're going to denote this collection of vectors as the sum of the subspaces. So we denote it as W1 plus W2, etc., plus WK, okay? Or we can also write it simply in short notation. So this is the sum over all I from 1 to k, Wi, okay? So again, remember, this is a set of vectors, yeah? All right. So we claim that this is a subspace of V, first of all. So this is also a subspace of V. Okay. I'm not going to check it now in detail, so I'll leave it as an exercise. You should check it yourself if you haven't seen it before. Yeah. So we see that this gives us a way to, given a bunch of subspaces of a given space, we can form a new subspace, which is the sum of the ones we were given. All right. So let's look at some example. Let's say V is the vector space R cube. Yeah. And let's take W1 to be the XY plane. Okay, let's take W2 to be the YZ plane. Okay, so if I draw it, let's see if I manage to draw it. So this is X, Y, Z. Okay, so the first subspace of the XY plane. So this is W1. And we have another one. So W2 is going to be the YZ plane. So it consists of all of this, right? So this is W2. All right. So then we claim that the whole space, R cube, is going to be the sum of these two. So R cube is equal to W1 plus W2. Okay, so why? Because we have that for any vector ABC in R cube, it can be written as a sum of vectors from these two subspaces, right? Because we have, for example, we can write ABC is equal to A 0, 0 plus 0 BC, where the first one belongs to W1, right? And this one belongs to W2. So every vector in the whole space can be written as a sum of vectors, of two vectors from the corresponding two subspaces, W1 and W2, right? So note, however, that this presentation is not unique, okay? So, but the presentation, the presentation of ABC as a sum of vectors in W1 and W2 is not unique. Okay, there are multiple ways to write the same vector in this form. Like, for example, we have that ABC can also be written as AB0 plus, let's say, 0, 0, C, right? So you see this is different from the previous, from the first way to write it, okay? So we don't have, even though there is always a way to write every vector in the space as a sum of two vectors from the corresponding subspaces, there might be more than one way to do it, okay? And so now we want to refine our notion of the sum of subspaces to ensure that every vector is presentable as a sum, but moreover, there's only one way to do it, yeah? So we want to ensure uniqueness in addition. And this leads us to the definition of the direct sum of subspaces, okay? So to fix this issue, the non-uniqueness of the presentation, we introduce a condition that assures uniqueness. So definition. Again, assume we have W1 through WK subspaces of V, okay? Then we say that V is the direct sum as opposed to just sum, yeah, the direct sum of the subspaces W1 through WK. And we will also write this as V is equal to W1. Now we have circle plus instead of just plus. Okay, so circle plus WK. If we have that V is the sum, first of all, okay, so we have it is the sum of Wi, and additionally, we have that if I look at the intersection of Wj with the other subspaces, so the sum over Wi for all I different from j, okay, then we get 0. And we want that this holds for each j between 1 and k. Okay, so we have this additional condition. Not only it is the sum of the subspaces W1 through WK, but also among these subspaces, if I pick any one of them, then its intersection with the sum of the other ones is trivial. It only contains the 0 vector. Okay, so the idea somehow to ensure additionally that the subspaces are orthogonal to each other. Okay, but let me not say that, just intuition. Okay, so let's look again at the example. What happens in the reals? So for example, let's take V to be R4 now. Yeah, one higher. And let's look at some subspaces. So let's write W1 to be the subspace given by AB 0, 0. Okay, so the XY plane. We can take W2 to be given by 0, 0, C, 0, where C is any real number. Okay, so this gives us the Z-axis. And we can take W3 to be 0, 0, 0, D. Okay, D in R. So this gives us the fourth axis of our four-dimensional space. Okay, then for any vector A, B, C, D in V, okay, we have the following. So we have that A, B, C, D can be written as a sum of vectors from these subspaces, right? So we can write A, B, C, D, let's say as A, B, 0, 0, plus 0, 0, C, 0, plus 0, 0, 0, D, okay? So this belongs to the sum W1 plus W2 plus W3, okay? So we see that every vector of the space can be written as a sum of vectors from these subspaces. So we conclude that V is the sum of Wi for I from 1 to 3, okay? But is it a direct sum? So let's check whether it's a direct sum. So we also have that if I look at W1 and I intersect it with the sum W2 plus W3, okay? So what is this going to be? So this is going to be the set of all vectors A, B, C, D, right? Now, because it has to be a vector in W1, it means that the third and the fourth coordinates have to be 0, right? So we have C equals 0, D equals 0, because it's in W1, but also because it's in the sum of W2 and W3. Let's look. So every vector in W2 has zeros everywhere except for the third position, and every vector in W3 has zeros everywhere except for the fourth position, right? So then this tells us that we have to have zeros in the first two positions for any vector in the sum. Okay, so then we conclude that also A has to be equal to 0 and B has to be equal to 0 because it belongs to W2 plus W3. But then there's only one vector with all zeros in all four positions. So we get that this is trivial, right? And arguing similarly, we also conclude that W2 intersected with W1 plus W3 is equal to W3 intersected with W1 plus W2 is trivial. Okay, so we conclude that in fact V is the direct sum of the W's. So W1, direct sum W2, direct sum W3. So here we in this example we do have the uniqueness of the presentation. All right. Okay, so hopefully these two examples illustrate the difference between just being a sum of subspaces and being a direct sum of subspaces. In the second case, we have uniqueness. Well, we haven't proved it yet, but at least we have the stronger additional condition, and we see that this guarantees uniqueness of the presentation. So this is going to be one of the statements in the theorem about summarizing various basic properties of the direct sum. This is theorem 510. Okay, so assume we have W1 through WK. These are all subspaces of a finite dimensional vector space V. Okay, so we have K subspaces of a given space. Then the following are equivalent. Okay. A, we have that V is the direct sum of the W's. This is the first condition. Equivalently, we have that V is the sum of the W's. Okay, and moreover, for any V1 through Vk with Vi a vector in the subspace Wi, so for all I between 1 and k, if we have that the sum of these vectors V1 plus Vk is equal to 0, okay, then in fact all of them are 0. So then Vi is equal to 0 for all I. Yeah. So whenever we have vectors from each of the subspaces, pick one vector from each of the subspaces. If their sum is 0, then they're all 0. Each of them is 0. This is the condition B. Now we have C, the uniqueness. So each vector V in the space V can be uniquely written as V1 plus, well, let's say as V is equal to V1 plus V2, etc., plus Vk for some Vi in Wi. Okay, so for each vector, because the whole space V is the sum of the W's, we know that it can be written, okay, but the equivalence for being a direct sum is that it's actually can be written uniquely. There's only one choice of the tuple V1 through Vk. which sums up to V. Okay, so this is the condition C. We also have the condition D. So if we have gamma I is an ordered basis for Wi, then we can take the union gamma 1, union gamma 2, etc., union gamma k, and this union of the basis for each of the Wi is an ordered basis for the whole space V. Okay. And the last equivalence for each I from 1 through k, there exists an ordered basis gamma I for the subspace Wi, okay, such that if we take the union gamma 1, union gamma 2, etc., union gamma k, what we get is an ordered basis for V. All right. So note the difference between D and E. They seem like close to each other, right? The difference is that in D, we are saying that for any gamma I, a basis for Wi, the union is a basis for V. Okay. So here it says for any. So for all gamma I, we have that the union of the gamma I is a basis for V. Okay. But in the condition in E, it's an existence statement. So we are saying that there exists a choice of gamma I such that the union of gamma I is a basis for V. Okay, so in D, we claim that for any choice of gamma i's, we get the union as a basis for V. In E, we're just saying that there is a choice of gamma i's. So it's a different statement a priori. Okay. Nevertheless, the theorem tells us that all of this is equivalent. So let's prove A implies B today. So we're going to show a sequence of applications, okay? I'm going to show that A implies B, implies C, etc., and that E implies A. So we're going to do the loop, the circle of implications, which will then show that indeed everything is equivalent on this list, okay? So let me just show that A implies B today. It's a quick argument, and then we'll finish the proof next time. So let's show that A implies B. Okay. So we have, by assumption, so assume A, right? We assume A. So we assume that V is the direct sum of the W's. So in particular, we have that V is the sum of W's. Oops. So for I from 1 to k. Right? Since it's direct sum, it's in particular a sum. And suppose, so we want to show B, right? So suppose that I have Vi, an element of Wi, such that the sum V1 plus V2, etc., plus Vk is equal to 0. So the sum is 0. Okay. Then for any J, we have that minus Vj. If I just express it from this equation, we get that minus Vj is equal to the sum over Vi for all I different from J, right? But this node belongs to the sum of the corresponding subspaces. So this belongs to the sum of the subspaces Wi over all I different from J, right? But also we have that the vector minus Vj belongs to Wj, right? Because Vj belongs to Wj, but hence the inverse, of course, also belongs because it's a subspace. So we have V minus Vj belongs to Wj, okay? Hence, we obtain that the vector minus Vj belongs both to Wj, but also to the intersection of it with the sum over all I different from J, Wi, right? Because it belongs to each of them separately from these two lines. But remember, since this is the direct sum, the intersection of these two subspaces is 0. Okay. So we conclude that Vj is equal to 0 for each j, right? Hence we get B. So B holds. Okay. So this shows that A implies B. A question, why should it be minus? It's minus because look, we have that the sum is 0, right? So then if I pick Vj here, so for example, let j be 1. Okay, so then I just need to express V1 from the other ones. So I move V1 here, so we get that V minus V1 is equal to V2 plus etc. plus Vk, right? That's how you get the minus. Yeah. All right. So, okay. So from this, we get that A implies B. And we'll show the other implications next time, okay? Thanks. So I'll stop here today. And I'll see you next time. Unless there are any quick questions before the end. Yeah.